Okay, so this week we start with some basic electricity concepts. First of all, the concept of voltage. Our definition of voltage is the average energy per charge. So in terms of units then, energies in joules, the units of charge are coulombs. So an energy per charge is a joule per coulomb, and that's defined as a volt. In terms of a relationship, we write the voltage is the energy, and this is generally electrostatic potential energy, divided by the charge. Now, to get an understanding of voltage, we imagine looking at a Duracell with microscopic eyes, and what we see is the negative end of the Duracell has got excess negative charge as a result of the redox chemical reactions. There are, of course, positive charges present, but there's an excess of negative. What makes the positive end positive is just a lack of negative charges. So that's our model then for a Duracell. Excess negatives at this end, and then a lack of negatives at this end. Now, obviously, like charges repel, so it's going to take work to move a negative electron from this end down to this end where they already are in excess. So that's where the stored energy is. The stored electrostatic energy is related to the work done in separating the charge. Now, if we come along and connect a wire to a voltage source, then these minus charges, excess minus charges, they are prevented from going this way by the chemical reactions, but they can go out into the wire, and that's in fact what they do. Because of the electrostatic repulsion, they're pushed out in the wire, and then that sort of causes a chain reaction where minuses get pushed all along the wire away from the minus terminal of the battery, of the cell. Now, of course, what'll happen is you'll build up a little bit of excess on this end, and then the flow will stop because any sort of push from the excess negatives on the Duracell, which would tend to make the charges go that way, that's going to be balanced by the push backwards from these excess minuses that have built up on the very end of the wire. So you get a momentary flow of charge, very momentary, on the order of 10 to the minus 10 seconds or something like that. If, however, the wire forms a continuous loop, then these excess minuses, some of them will get pushed out in the wire, and that will push all the minuses in the wire because they are repelled. I should mention, of course, that the positive nuclei and inner electrons don't move in a metal. It's the minuses that are free to move, and so it's the minuses that are moving all the way around the wire back into the positive terminal. Then the chemical reaction kicks in again and creates other excess electrons at this end. So now you get sustained flow of charge, and the sustained flow of charge in a circuit is known as current. Now, current is the amount of charge flow per given time. Units then, this is charge in coulombs, this is time in seconds, so coulombs per second is defined as an ampere of charge, given the letter capital A. So that's voltage and current. We can think of an electric circuit as sort of like a ski hill. Here we've got the cell, which provides energy to the circuit and which pushes charges around and makes things flow. And on the ski hill, the chairlift gives skiers energy, and then from that point on, it's gravity that makes them flow around down to the bottom. Just like electrostatic forces make the charges flow in this circuit once they've been separated. So the energy here, well, for the circuit, it's the voltage, or the cell. That's where the energy comes from. Here, of course, it's the chairlift that provides the energy to go skiing. The flow here, well, this is the current. And on the ski hill, it's just the skiers per second that are flowing up and down the mountain. Now, in this circuit here, there was a little wiggly line, and you probably know that refers to a resistor. Every circuit offers some resistance to the flow of charge. And what happens is, in a circuit element, say like a lamp, the charges that are flowing through undergo collisions and as a result lose a lot of their energy. Their flow is impeded by those collisions. So that's why we have these wiggly lines as a symbol, because it's sort of a visual, I suppose, of a bunch of collisions happening as the charges flow through that device. Now, this device could be a lamp. As I said, it could also be a piece of wire. However, metal wires, have a very, very low resistance. So there is some resistance here, but very little. This could be a lamp or a motor or just a standard lab resistor. Now, when the charges flow through then, because of the collisions, some of their energy, some of their voltage is transformed to heat. So you go from higher voltage to lower voltage, but you don't lose any charge. So the current will be the same. It's the energy or the voltage that's changing. Now, the amount of flow that's going through a circuit depends on the total resistance and the voltage. This is known as Ohm's Law. If we have lots of resistance, there's not going to be very much flow. With not very much resistance, you'll have a much higher flow, which suggests that the amount of current flow is inversely proportional to the resistance. So large resistance means low flow, small resistance means large flow. At the same time, the amount of current flow is proportional to the voltage drop. If you've got a lot of charge separation, there are lots of quote-unquote electric pressure, that's going to create a lot of flow in the circuit. And conversely, with less charge separation, less stored energy, you're going to have a smaller flow, which suggests that the amount of current flow is directly proportional to the voltage. Now, that in word equation translates to I is V over R, or as it is more commonly written, V is IR. This is the statement of Ohm's law. Now, R is the resistance of the circuit element, and if you solve for resistance, you'll see it's a ratio of a volt per amp. And something that conducts really well is going to have a low resistance. Something that's a good conductor is going to have a small resistance. Sorry about the skill saw going on in the background. I'm actually recording this at my cabin, and somebody's working on a deck right now. Now, in the ski hill analogy, resistance is like the depth of the snow. So really deep snow is going to slow down the skiers. Hard packed snow, which is low resistance, is going to give us a lot more skier flow. Ohm's law for ski hills just says that the skier flow, which is the current, varies directly with the height of the mountain, that's like the voltage or the energy, and inversely with the depth of the snow. So the world's simplest examples, I is V over R. This is a 6-volt cell over a 25 ohm motor. That is going to be 0.24 amps of current. If, on the other hand, we forget to connect the motor or we don't connect it properly, then our 6-volt cell is applied only to the wire, which has a resistance, but a fairly small one. And if the cell were able to provide it, you get about 6,000 amps of current. Now, energy interests us. So the energy in a circuit, well, we said voltage was energy per charge, so that means energy will be charge times voltage. If we rearrange our voltage definition, we get energy as charge times voltage. Now, of course, power is going to be energy over time. Energy over time. But we're just saying that this energy is charge times voltage. That's divided by time. If we rearrange that a little bit, I'm going to write it as voltage times charge over time. And charge over time is, of course, our definition of current. So we find that electric power is the product of voltage and current. Now, power should have units of watts, of joules per second. Let's check that out. So we have a voltage, which is an energy per coulomb, and then we have a current, which is coulombs per second. So voltage will be joules per coulomb, and current will be amps, or coulombs per second. So we see that electric power does indeed have units that are consistent with joules per second, or watts. So to summarize then, electric power is the product of voltage and current. Now typically, household appliances will have power ratings in watts. So a typical rating for a hairdryer might be 1200 watts. As well, typically in the household, the voltage is 120. So you can find the amount of current that's flowing through the wires of your house and that current will flow through the wires of the house, out through the outlet, through the plug, through the braided wire that takes it to the hairdryer. It'll flow through the heater and the fan here, and then it'll flow back out the cord, into the plug, back into the outlet, and all the way into ground. So rearranging this statement here, if power is the product of voltage and current, we know current will be the ratio of power to voltage. So we have 1200 watts, 1200 joules per second used by that hairdryer, 120 volts, 120 joules per coulomb of energy. That means that hairdryer is drawing about 10 amperes of current, which you may know a household circuit's limited to 15 amps, so you could only plug one of these hairdryers in. If you plug in two, you'll pop a circuit breaker. So that's the first thing we wanted to talk about, basic circuit concepts. And we've introduced voltage, current, and resistance. Voltage, current, resistance. We've talked about electric power, and we've had two relationships, Ohm's Law, V is IR, and then electric power is the product of voltage and current. Now, something a little bit different and quite important here, conceptual. How do we go about making electricity? Well, it turns out there's something known as the induction principle that says you just need three things. You need to take a magnet, then you need to have some wire, usually a coil, and then you need to move the magnet around. And if you have those three things, you'll get electricity. So we're going to watch a little demonstration of that. So I'm just going to take a magnet and I'm going to move it around in a coil, and then I'm going to have a very, very sensitive current meter that's going to detect the flow of current in that coil. Okay, so as we saw in our demonstration, a magnet or an electromagnet moved next to a coil creates voltage, induces voltage in this pickup coil. So there's really two coils. There's the electromagnet and the pickup coil. Now, if you look at an electric generator, you'll see exactly those two sets of coils. Here are the rotor coils. Okay, those are the magnetized magnet electromagnets right here that are moving around. And then on the outside ring of the generator, there are static, non-moving pickup coils, and that's where the voltage gets created. So you just need the magnet, that's the rotor electromagnet. You need the coil, that's the stator coil right here, and then you need motion. Now, what makes the rotor spin? Well, there's a number of options. One is, of course, the water flow through from a hydroelectric dam. Another would be steam pressure from thermal power. And you can use nuclear reactions to make heat and make steam. You can burn coal to make heat and make steam. You can burn natural gas to make heat and make steam. There are a number of choices for getting that heat energy, that thermal energy, to make the steam that pushes on the turbine. Now, once you've made that electricity at your power plant, you want to transmit it to where it's needed, which is the cities. Now, the energy that we're making is typically thousands of volts and thousands of amps. It's transformed. We pass it through a bank of transformers before transmission. Now, what are transformers? Well, they're not robots in disguise. They're electrical devices that transform or change voltages, okay? They're for changing a voltage. Now, we use lots of these in our daily life. You plug in a charger, that takes the 120 volts that comes out of the wall and steps it down to a voltage that your device can handle. Probably somewhere on your street, you'll have either a pole-mounted transformer or a metal box on the ground transformer that's taking voltage from transmission voltage down to house voltage. Now, I mentioned the word already, step up and step down. Step up transformers increase the voltage, and we do this at the dam. We step up the voltage for transmission. Then when it arrives in the town, we step it down. First of all, at the local substation, to sort of a local voltage, and then ultimately in the residential area to house voltage. Now, the way that these work relies on the induction principle. It basically, the amount of volts that you have depend on the number of wire loops in your transformer. So we're going to have an input and an output, and the input volts depend on the number of loops N on the input side. The output volts depend on the number of loops on the output side of the transformer, and I'll show you a picture in a moment. But because a transformer can't make energy, And because power is the product of voltage and current, if the voltage is going up, it must be that the current goes down, which suggests an inverse proportionality between voltage and current. So this is known as the transformer equation. It's basically a series of three ratios. So if we look at, say, a typical dam where we're producing 750 volts and 500 amps, we want to find the power. Well, power is still the product of voltage and current. So we have 750 volts and we have 500 amps. That's going to be 37. Now let's see, I got to count all my zeros here. So 1, 2, let me pause that for a second. Okay, so I need 4 zeros here. 5, and then 1, 2, 3. So that should be 375 kilowatts of power coming from that transformer. Okay. So now, if the transformer... All right, so here's an example. We have a dam producing 750 volts and 100 amps. First task, find the power generated. Well, power is the product of voltage and current. 750 volts times 100 amps gives us 75,000 watts, or 75 kilowatts. Now, let's imagine that at that dam site, the voltage is boosted up by a factor of 100. So this is a step-up transformer. That means that the output voltage is going to be 100 times the input voltage. So that means it's going to be 75,000 volts, or 75 kilovolts. Now, based on the argument we just made, if the voltage goes up by 100, the current's going to go down by 100. So we're only going to have 1 amp of flow leaving the dam through the transmission lines. Now, transmission lines are made of metal, but if you get 1,000 kilometers of metal, it is going to have some resistance, and therefore there'll be some energy lost along the way. Let's imagine that those transmission lines were 2 ohms each. And let's see how much energy we would lose in them. Well, there's only an amp flowing through those lines, so we're only going to lose 2 volts across each one. So then in terms of the power that's lost, well, it's going to be 2 times 2 volts, 4 volts, and an amp. You're only losing 4 watts of power. So at the city, you had 75 kilowatts to start with. You lost just 4 watts in the transmission lines. So you've lost a very, very tiny fraction of a percentage of the energy. Now let's see what would happen if you hadn't transformed it all. And so now your 100 amps is flowing through those 2 ohm lines. So here's your dam. There's your transmission lines. No transformer. So we've got these 2 ohm lines, and there's 100 amps of output from the dam flowing through these transmission lines. Well, the voltage drop is going to be 200 volts for each one. So in terms of the power loss, there's 400 volts times 100 amps, 40,000 watts. So you've now, of the 75,000 watts you generated, you've just lost 40,000. And there's only 35,000 watts that are delivered. You lost half the power in the transmission lines. This is why we transform. Because when we step up the voltage, the current goes down. When the current goes down, the line losses go down, and the power grid is much more efficient.